Swayam Prabha. Digital India. Educated India.
With the basic understanding of all the thermodynamic parameters and knowledge of working of calorimeters, specifically the calorimeters which are designed to study the reactions of biochemical interest, we have discussed at length how these calorimeters can be applied to study protein-ligand binding. Isothermal titration calorimetry, as we discussed in earlier lectures, is able to give thermodynamic signatures associated with the protein-ligand binding in just one single experiment. Then we also discussed how to design experiments to understand the nature of interactions which are responsible for the binding. Identifying the nature of interactions is very, very important, as I have been repeatedly discussing, that if we can understand the nature of interactions, then the nature of interactions can be connected with the functional groups on the drug molecules which are responsible for binding. And once we identify the functional groups in connection with the binding affinity and the other thermodynamic signatures, then these give us guidelines for rational drug design. The next question comes, can we use isothermal titration calorimetry in identifying the sites for drug protein interactions, and how a combination of isothermal titration calorimetry and differential scanning calorimetry can give further information not only about the thermodynamic signatures, but also about how the protein unfolds in the presence of ligands. When we talk about thermodynamic signatures and associate the affinity with the standard reaction Gibbs energy change, then automatically that standard reaction Gibbs energy change takes into account the changes in enthalpy and changes in entropy. Enthalpy-entropy compensation phenomena is another aspect which has to be kept in rational drug design. And in this lecture, we will also discuss about enthalpy-entropy compensation and its possible sources of origin both in protein-ligand binding and in unfolding of proteins when studied by variety of methods. Now, let us take a look at how to interpret the DSC of protein-ligand complex. As discussed in one of the previous lectures, let us take a look at this slide. When we thermally unfold a protein P, then we can find out its transition temperature, calorimetric enthalpy, etc. And when the ligand is bound to the protein and you unfold PL, usually its unfolding will be at higher temperature. And we will get the corresponding thermodynamic parameters associated with the unfolding of PL complex. Now, this kind of situation will arise when the protein is fully saturated with the ligand. What I mean is, PL showing only one peak, this kind of situation will arise when the protein is fully saturated with the ligand. Now, let us take a look at, if you thermally unfold only the protein, we will usually get a single endotherm. Two lines are shown over here. One line shows the experimental data points and the second curve shows the fitting of a suitable model to the experimental data points. Now, let us take a look at the next figure. It is possible that sometimes we may get this kind of DSC profile for a protein ligand complex. In the previous lecture, in the previous slide, I showed only one endotherm for a PL complex, but here I am taking another example where PL complex may show like this kind of endotherm. The overall endotherm is the black solid line, and we can clearly see that it is not symmetric endotherm, especially when we look at the right hand side. The curve deconvolution shows that there are two endotherms embedded under this overall endotherm. These two endotherms are shown by the dotted lines. Now, what could be the reason for these two endotherms? Let us discuss that what is usually the meaning of one single endotherm, or what is usually the meaning of two endotherms which are deconvoluted under an overall single endotherm. When do we get the two endotherms? One possibility is when the protein has two domains and both the domains are unfolding independently, one after the another, you will get two endotherms. The other possibility is that in the protein ligand complex, if there is unsaturation, or in other words, if all the binding sites are not saturated, then what will happen? Let us take a look at this reaction. If you study P plus L and this forms PL, and if at equilibrium you have sufficient amount of PL and sufficient amount of P, and then when you heat this, you have these two reactions going on, P going to P denatured and PL you are heating, it is P denatured plus L, and one will get a transition corresponding to P and transition corresponding to PL, and depending upon how close they are, either it will be showing in the form of a single endotherm with a shoulder, or there will be two well separated endotherms. Now, let us go back to the slide and take a look at this DSC curve. One way of interpreting this kind of DSC curve is that at equilibrium there are sufficient amounts of both PL and P which are showing up as two separate transitions. The one which is at higher temperature can be due to the PL complex unfolding, and the one which is appearing at a lower temperature, that is corresponding to the protein which is still unligated. Now, let us take a look at this figure. These figures correspond to DSC scans of thermal denaturation of bovine serum albumin at pH 7.4 in the varying molar ratios of tetracycline to BSA. This one is without any tetracycline. This is in the presence of tetracycline. We can clearly see that when you add tetracycline, we see that the overall peak is no more kind of symmetric peak, but there is a shoulder which could be due to the unfolding of the protein ligand complex, and the other one can be the one which is still not ligated. Then there are two more figures C and D shown over here, and C and D correspond again to the one which is without any Rowley tetracycline, and this is in the presence of Rowley tetracycline. And again we can see here that the one peak is now divided into two peaks. That means again showing one of the interpretation to such a behavior can be that at equilibrium we have both the PL and P, and that is why it splits up into two endotherms. And this table shows the corresponding data. That means it is possible to get T half and delta H for each endotherm, and then once you have the transition temperatures and enthalpies associated with each endotherm, then more insights into the thermal unfolding of the protein can be discussed. So, this is about that when a protein is ligated with a ligand, and when you thermally unfold it, it may show it one endotherm, it may show two endotherms, and the situation can become more complicated if the protein has more domains and those domains are unfolding independently, and even complexity can further come if the ligand binds to one particular domain and the other domain is unfolding in an independent manner. Now, let us take a look at the next slide. Human serum albumin, HSA, as we discussed earlier, because of its structure, because of its properties, can bind variety of ligands. One such ligand which binds to human serum albumin is fatty acid. Fatty acids can find variety of sites on human serum albumin or bovine serum albumin and show a significant amount of binding. And these binding sites are seen in this picture, FA1, FA2, and all other fatty acid binding sites possible are shown over here. In addition to the fatty acid binding sites, there are well defined other drug binding sites on serum albumin, and that is why if we are interested in understanding the binding of a certain ligand with this transport protein, serum albumin, we must work with the fatty acid free protein, because if we work with the protein which already has fatty acids, then that will affect the binding studies. If we work with the fatty acid free serum albumin, then we can design experiments to understand that at which binding site the incoming ligand is binding. Let us take a look at the next slide. This is the structure of serum albumin, and as we have earlier discussed, there is a warfarin binding site, then there is a diazepam binding site. Several ligands bind to warfarin binding site and several ligands bind to diazepam binding site, and it depends upon the molecular structure of the incoming ligand. For example, take a look at the molecular structure of warfarin and also of diazepam. Now, how to design the experiments? We have well defined warfarin binding site, we have a well defined diazepam binding site. And these two molecules, warfarin and diazepam, can be called site markers, because it is well established that warfarin binds to pseudo site 1 and diazepam binds to pseudo site 2. Now, how to design the experiments? What one can do is, in identification of the binding sites, is that you make a complex of warfarin with serum albumin and study the binding of the other drug, the main drug which we want to understand where it binds. We will already have in hand the binding constant and other thermodynamic signatures associated with the binding of warfarin with the protein. Now, if the binding site is already occupied by warfarin and the incoming ligand does not bind at this site with an affinity which is much higher than warfarin. What in other words mean is that if the binding affinity of the incoming ligand is less than the binding affinity of warfarin for site 1, it will not be able to displace it. Therefore, it will not bind, it will not show binding. And once you remove warfarin from that site, we titrate with the free serum albumin, it will show binding at site 1. In other words, it shows a binding at site 1 in the absence of warfarin, but in the presence of warfarin, it does not show binding. That establishes that the incoming ligand is binding at site 1. Similarly, another experiment can be designed by blocking site 2 with diazepam and then doing these kind of experiments. So, this kind of combinatorial experiments help in identifying that at which site out of these two, site 1 or site 2, the incoming ligand is binding. Therefore, thermodynamic signatures which are obtained by the use of isothermal titration calorimetry can also help us in identifying the binding sites of the protein. So, when it comes to identifying the binding sites, for example, by using a similar approach, it can be established whether the incoming ligand binds to site 2 or site 1. And in order to arrive at this kind of result, as I just discussed in the previous slide, that we need to do experiments with the site markers and see whether the binding signatures are affected in the absence and in the presence of the site markers. Okay. What else we can understand by applying a combination of isothermal titration calorimetry and differential scanning calorimetry? Isothermal titration calorimetry and differential scanning calorimetry will give you the thermodynamic signatures and will also give you the thermodynamic parameters associated with the unfolding of proteins. Conformational characterization of the protein can be done by the use of fluorescence spectroscopy and also by the use of circular dichroism spectroscopy. So, therefore, if we study the binding and unfolding process by using a combination of isothermal titration calorimetry, differential scanning calorimetry, UV visible spectroscopy, fluorescence spectroscopy, circular dichroism spectroscopy, we can discuss the mechanism of binding as well as the thermal unfolding of protein in great details as seen in this slide. Let us take a look at this slide. This slide shows the binding of ketoprofen, which is an antipyretic, anti-inflammatory drug, to serum albumin. By the use of isothermal titration calorimetry, the binding site of ketoprofen on serum albumin can be identified. That means we can address this step where the ligand is going and binding. And then when you study the thermal unfolding of the protein, of the bound protein, and we can see that there are two well defined endotherms embedded under an overall endotherm in the presence of ketoprofen. These results suggested that these two domains of serum albumin are unfolding independently, where the bound domain is unfolding at the higher temperature and the unbound domain is unfolding at the lower temperature, and that is why we are getting the two transitions within an overall broad transition. For further details on the mechanism, I refer you to this research article. But what I want to highlight over here is that by combining the calorimetric and spectroscopic techniques, these kind of detailed mechanism can be postulated. Now let me talk about the enthalpy-entropy compensation. Whether we talk about the protein-ligand binding or we talk about the thermal unfolding of protein, in both the cases we are talking about the enthalpy changes, we are talking about the entropy changes. The enthalpy changes and entropy changes both can be used to further get the standard reaction Gibbs free energy changes. Let us take a look at the slide. We have delta G naught is equal to delta H naught minus T delta S naught. Delta H naught, the negative value of delta H naught assists more in the spontaneity of the process, and the positive value of delta S naught assists in the negative value of delta G naught, or in other words towards the spontaneity of the process. Now, it is a combination of delta H naught and delta S naught which will decide the overall effect of delta G naught. In the rational drug design, suppose if we are able to achieve the desired delta H naught, what I mean, if the desired delta H naught should be more and more negative. Okay, if we get sufficiently negative value of delta H naught, but that is offset also by the negative value of delta S naught, then overall the net effect on delta G naught will not be significant. In other words, if the enthalpic gain is being offset by the entropic loss, then in pharmaceutical industries it will lead to frustration towards getting more affinity. So, therefore, towards a rational drug design, the efforts have to be that we achieve a better negative value of delta H naught and not much compromise on the loss on conformational degree of freedom, not much loss on the entropic front. Enthalpy-entropy compensation has been a subject of discussion for a long time. Enthalpy-entropy compensation has been observed in many phenomena like protein-ligand binding and the protein unfolding, along with some other processes where there is a change in delta H naught and delta S naught. Although there have also been reports in literature that in certain class of compounds enthalpy-entropy compensation has not been observed. Some authors have even pointed out or questioned the enthalpy-entropy compensation and have hinted or pointed out that the compensation is occurring due to the errors in delta H and delta S naught, and it is not a real phenomena. Anyway, there are still papers appearing on the validity of enthalpy-entropy compensation, but a straight look at this equation delta G naught is equal to delta H naught minus T delta S naught does suggest that in order to get more negative value of delta G naught, delta H naught has to be negative and delta S naught has to be positive. And if there is an enthalpy-entropy compensation, if there is a complete compensation leading to no net gain in delta G naught, then the efforts can be frustrating. Let us take a look at the slide. Enthalpy-entropy compensation is the tendency for changed interaction to produce more negative delta H naught, which can be associated with more negative delta S naught. Usually it is observed that you gain in enthalpy, but you lose in entropy. Let us take a look at the next comment. Increased bonding produces more delta H naught values, and these tend to occur at the expense of increased order, hence more negative delta S. So, this is the reason for the compensation, because if two molecules interact favorably, delta H naught will be negative, but also there is a loss in entropy. Let us take a look at the next comment. The engineered enthalpy gains can lead to completely compensating entropic penalties, thus frustrating ligand design, and this is exactly the point that I was making. Next comment, complete compensation would mean that modifications made with the intent of improving the enthalpy of interaction, such as the introduction of a hydrogen bond donor, would be counterbalanced by unfavorable entropic contributions, leading to no net gain in affinity. Now, let us take a look at physical origin of enthalpy-entropy compensation. Based on literature review, the enthalpy-entropy compensation in case of protein-ligand binding I have just discussed, that negative value associated with the formation of favorable bonds for polar bonds is also happening at the expense of the decrease in the disorder or increase in order. The other reasons which have been proposed in literature is, one is solvent reorganization may also be one of the sources for the compensation. Conformational restriction of bound states is not universally compensating, and receptor flexibility may be a source of compensation. In conclusion, enthalpy-entropy compensation phenomena cannot be ignored, because especially in pharmaceutical industries, if we are interested in improving the affinity, then the contributions of delta H naught and delta S naught make a big impact in getting a more negative value of delta G naught. So, in this lecture, what we have discussed is that how the use of isothermal titration calorimetry and differential scanning calorimetry together can help us in not only describing the protein ligand binding in full details, but also in understanding how this process or what is the mechanism associated with the unfolding of the protein in the absence and presence of the ligand. We further discussed the significance of enthalpy change and entropy change in overall delta G naught and the phenomena of enthalpy-entropy compensation, which cannot be ignored. We will further discuss that although thermodynamic signatures associated with the binding of a ligand with protein can be determined by isothermal titration calorimetry successfully, but when it comes to very high association or the associations which are associated with the very high values of the affinity or K, then differential scanning calorimetry becomes very important, and this we will discuss in the next lecture. Thank you very much.